storage. What's this? Put a red circle around here. What's that piece? Well, some people interpret that to be the storage piece. And my belief is that's not correct because of the way you look at it. If you go do some simulation and you just build yourself a numerical simulator, well bored and simple, keep it simple, a region of damage around it, and then something that describes the reservoir outside that. So I've got a region that's got low KH here, low KH, love all these colors. Oops, screwed up. And high KH out here. Better put the right caps back on the right ones, huh? Just build a numerical simulator to generate that, to see what that signature looks like. The permeability, the KH you'll get for this piece, matches this piece. So I would assert to you that this actually is, if I were to calculate the slope through there, that's the KH associated with the damage region. It's not storage. Now, many times the damage is so small that this lasts just literally for minutes, hours at the most. So it kind of disappears in the effect of the storage. The next piece of the puzzle is then, what's this last piece? There, I've got a blue one, that's going to be fun. What's this part? Well, that's the far distant reservoir piece. That's this piece out here. All right? Now, the problem is, management allowed me to have 72 hours. I can shut the well in for 3 days. A 3-day shut-in, if I'm lucky, I'm going to get a lot of signature in that reservoir piece. I'm hoping I'm lucky, but the fact is I'm probably not so lucky. So, let's think about what that might mean. I calculated my XF. All right, I calculated my XF, I've got a nice KH, and I want to get a P star. Where do I measure P star? Right? Well, not the log. T sub H approaches 1. Log of T sub H goes to 0, right? It's this point right here. I want to measure this thing I call P star. If the well's been on production for a couple of years, this graph is not sitting here. It's sitting way over there someplace. Yeah? The longer the well's been on, the bigger T sub P is, the further to the right that graph moves. Well, that means that if I make a little bitty screw up here, I could literally make 1,000 pounds of error in P star, couldn't I? It becomes very, very sensitive. That really creates a problem. Your management wants you to tell them how good their reservoir is. Yeah, it's really good. Oh, it's a really good reservoir. So I'm going to use a really shallow slope through here because that predicts a really good reservoir. Oh, that means my P star is small. If I were to interpret it out here with a steep slope, I get a nice high P star, but a terrible looking reservoir. I have this conflict of interest problem. A Horner plot creates a conflict of interest. Yeah, because, I've kind of drawn this a little goofy here. Let me try again. There we go. I could put a steep line through it and get a high P star, or I could put a shallow line through it and get a low P star. The shallow line is going to tell me how good the KH is. I'm going to have a really good reservoir, but I do not have a high reservoir pressure. Well, what I just told you was, you want a good reservoir, you got to have low KH. Or you want a good reservoir and have a high KH. Well, having a high P star is going to imply that I got a big EUR, right? The higher the pressure, the larger the estimated ultimate recovery. A low P star implies that I've got a low EUR, but I have a good reservoir. So I've got a problem. But the bottom line is, the tail end of the graph, if it's still curving, to get a P star from it that's useful is very difficult. All right? You came back. You just wanted to hear more jokes, I know. Forgive me for teasing you, but what's up? Okay? Anyway, what we're looking for is this last piece as a measure of the reservoir quality in exactly the same manner as we're looking for production data. You have good hourly data for 2 weeks. That may be more useful than 2 years of monthly data. It is amazing. And the sad thing is, everybody says, oh, that early data is junk. It's no good. Man, I really disagree. That early production data, when the well is cleaning up after the frac job or after the acid job, that data can tell you more about the job that was done, what you paid money for, than waiting 2 weeks to start collecting data. Hourly flowback data by a flowback crew that knows what they're doing can be so valuable because it tells you how good it was, how good it should be, before somebody screwed it up. And I mean that with, if you can't tell the passion in my voice about it, then I need to stand up and tell you passionately how important I think that is. Historically, this industry has not believed that that data was useful. I am adamantly convinced that it is incredibly useful because it tells us what the service company accomplished prior to the operations screwing it up. I dropped the computer or something on the floor there. Is it? Anyway, so let's start by looking at early time signatures. And the reason I want to talk about it in terms of the signature idea do I need to use a microphone? I hate using that thing because every time I move my arms and squeal at you. Is that all right? The guys on the back row seem to be tuned in pretty well. Except when they start. Would you please hold the snoring down?
I'll try.
Okay.
No guarantees.
No guarantees. I know. I understand. I understand how that works. Okay. All right. Early time signatures. Prior to a dimensionless time of 1. Now, why did he use a dimensionless time of 1? In the real world, if you're looking at wells, well, I'll be specific. If you look at some of the wells in Kuwait, dimensionless time of 1 is literally about 10 minutes. Okay? Very, very quick. Because the wells are very high conductivity. If you look at stuff in the Gulf of Mexico, you're looking at dimensionless times of 1 being 10, 20, 30 minutes at the most. If you look at wells in Green River, Wyoming, dimensionless time of 1 may literally be a month. Okay? So to say dimensionless time of 1 in our time is not a very meaningful statement because it can cover, when you just think about the reservoir quality question, that PERM term up there, and the storativity, Powder River stuff, for example, that porosity is going to be in the range of 10%. The stuff in the Middle East is going to be porosities in the range of 20%. Okay, so you've got a twofold difference just in the pore volume right there, boom. Not to mention a 1,000-fold difference in the permeability of the system. So when we talk about how much data it takes to have an interpretable data set, stuff in the Middle East or the stuff on the Gulf Coast has the same data, has the same signature, it just has to be measured differently. All right? Stuff on the Gulf Coast, if you don't have pressure data by the second, stuff in the Middle East, if you don't have pressure data by the second, you don't have a usable data set. In Wyoming, western Colorado, Eagle Ford in Texas, Avo, etc., Morrow, Springer, if you have data by the day, you have a very high resolution data set, simply because of this definition of dimensionless time. All right? So you say, well, my reservoir can't work. No, I didn't say that at all. I said you get the data recorded at the proper resolution, and you will have a usable data set. All right? So it really isn't about, well, it is about the instrumentation, because you've got to have instrumentation good enough to record the data fast enough to match the properties of the system. So early time, dimensionless time less than 1, but that idea covers a huge range of real value times. Please.
Is that kind of resolution difficult in older fields?
No.
No, they still have, they have that kind of.
The problem is not, sorry, go ahead.
I was gonna say, they have that kind of technology where they can
Sure.
measure radian per day.
The problem is this muscle, that muscle between your ears, their ears. It is perceived that that data is A, useless, and B, impossible to obtain. Neither statement is true, in my opinion. I gotta tell you, and I mean this with absolute sincerity, the best opportunity for new oil discoveries is not Texas, it's not Oklahoma, it's not Kuwait, it's not Saudi Arabia, it's West Virginia. West Virginia, of all you think, come on. West Virginia has something in the order of 150,000 old well bores that have been abandoned, that had known oil production in them. The technology in West Virginia is a screaming -1 out of 10. It is. It's sad. And because that perception, the point you just made, because of that perception, the opportunity there's no geologic risk whatsoever. The opportunity to use some intelligence, in every sense of the word, is just out of bounds. You know, you'd say, oh, maybe that's not so good. Yeah, well, okay, how about southeastern Kansas, northeastern Oklahoma, Kentucky, Tennessee? You know, these are old. Well, one of the really weird points of history. Do you know why Kansas City came into existence? The city of Kansas City, not the city of Independence, Missouri. Independence, Missouri came into existence because of the Oregon and the Santa Fe Trail. The Oregon and Santa Fe Trail started in Independence, which is, 40 miles east of Kansas City. Independence was all about the trails that led west. Kansas City was the Houston of 1910. There's an old field there called the Rantoul Field, the Paoli Field, and the Polo Field. Those were 3 very prolific oil fields back at the turn of the other century. Kansas City was the oil capital of the U.S. for about 30 years. Little known fact, utterly useless, but the point I make to you is, if you go back and look at the history of these places, right to the heart of your point, those places have never had sophisticated technology applied to them, and it is perfectly applicable. Yeah, okay. Early time. The pressure wave is in the wellbore still, or at the very least, it's in the fractures near the wellbore. It has not yet significantly moved into the reservoir, all right? So, this pressure wave, this ellipse I've been pushing on you about, has not even yet developed, okay? It's just barely starting to happen, but most of the transients are in the wellbore. So we are at early time. On the type curve that we're going to look at in a second, look at there, the infinite acting radial, the infinite acting elliptical, okay? I don't believe a radial system exists anywhere except in here. Well, okay, on the notes that you had to take in your pressure transient class. They don't exist. This is the curve that describes the behavior of an anisotropic, unbounded system. But what happens is this. As the anisotropy gets worse and worse and worse and worse and worse and worse, and ultimately horrible, this line forms. This is the theoretical solution for a linear flow system. The half-slope line on that. The unit slope lines have 2 interpretations. The unit slope line at late time, up here, is the solution for pressure response of a boundary-dominated system. It's gone into pseudo-steady state, all right? The other scenario is a unit slope line that forms early, which is wellbore storage. Once in a while, and I've seen a few of them, once in a while, you'll see this thing form a storage line, and it goes straight into boundary-dominated. There's literally no reservoir response. What does that mean? What does that mean? How could that happen? There's actually quite a simple answer, but how could that, think about it, wrestle with that a minute. This well was in storage, something approaching a unit slope line early, and and just forgot to go into the reservoir dominated piece and went right straight to pseudo-steady state. Did he? Could that happen? If so, you're an engineer, and you're receiving this wonderful $437 million a year. Really nice salary, hey. How? Crafton, it's your reservoir. You manage it. What did it do? I got to go to the board tomorrow morning and tell them. What did it do? Because I've seen that signature. Now, in the Horner plot context, remember the straight line I drew? It's that. How did that happen? Come on. Somebody got a high, I mean, the nice thing about engineering, ain't nobody wrong, as long as you can defend what you claim. There are only two professions that can bury their mistakes. Us and the medical doctors.
Do you have too many wells that are too close together? So they're seeing...
Could be. Yeah, that's a possibility. Too many wells. The wells are on too dense a spacing, so they're basically going into interference immediately. Yes, that is a possibility. Others? See, that's the fun about engineering too. There ain't no one single answer. So give me some other hypotheses. One of them is that the data is wrong. Obviously. The pressure gauge was stuck. Hello? So we've got to consider the possibility that we had instrument error. That business about REPSA. Repeatability, precision, system error, accuracy. So REPSA is a possibility. There is another one that's important. Burry and Cox talked about it. Burry and Cox told us that they were able to replicate what appeared to be boundary dominated because of onset of time-dependent skin. So that's the third possibility. So one is interference, right on. Another is instrument error. And the third is the possibility that the well has been damaged so quickly and so severely that it never exhibited a reservoir signature. All right? So there are several scenarios that could apply. But as the well goes from manageable anisotropy, it gets worse and worse and worse and worse and worse and worse, to the ultimate condition of anisotropy, which is linear flow. When it's in linear flow, when it's log-log plot of dimensionless time versus dimensionless pressure, or dimensionless potential, it will exhibit a half slope or spur of time response. Okay? So that's the transition we're looking for. And there it goes again. Okay, Rod, do your magic. Okay, good. Do not buy a Kensington. Good, it wasn't just me. Okay, that did better than I got. What'd you get? No, it ain't that. All right. There we go. Now, okay, is that you or me? What'd you do?
Turn it off and on.
Oh, that's too easy. All right, there we go. All right. In the center, think of this guy as a Horner plot, except I'm going to call it a Nicky H plot. This early time piece to the west of dimensionless time of 1, right there, that's this piece of the signature. There's that straight line we're looking for. Why did this not generate a straight line? Well, it's because on this graph, this piece right here is this piece. That sharply curving piece there flips over when I plot it in a semi-log setting. But they are the same piece, okay? So that early time, the really early time, is this curving piece right here. It has not been on production or shut in. The transient hasn't been in existence long enough to satisfy that log approximation, all right? Thanks, Ryan. Ooh, there we are back in the middle of the swamp. Microseismic data. The early time, this pressure wave is still moving where these dots are. It has not yet moved into the reservoir beyond it. What you see is this kind of a signature. Oh my gosh. Whoa, hang on. So, when I have a significant, what's referred to as a stimulated reservoir volume, the SRV, Anytime you go to the meetings and somebody's trying to show off about how wise they are, my SRV is, get right on it. All they're talking about is the extent or size or volume associated with the microseismic events, all right? So, the size of the microseismic events creates this signature. And that I have come to believe is an extremely important signature. In many wells, and I learned this lesson in the Marcellus, in many wells, this signature arises because the extensiveness of the natural fracture system. A really large natural fracture system will create this early time signature, not parallel to anything on the log-log plot. But when you look at it on the semi-log plot, you see this transition. Well, that's anisotropy in the extreme. That's exactly what anisotropy looks like, all right? So this shallow slope is the permeability of this natural fracture system. The change point here, right there, where it switches from the natural fractures to the matrix, that's the pore volume of the natural fracture system. Because some wells, as you get into this and look at as many of them as I have, you'll see that some wells will have a little bitty short, small portion like this shallow, and then it'll break steep. Some wells will literally go 5 or 6 log cycles before they break over. Invariably, the best wells are the ones that break over the latest, the furthest to the right. That pore volume, and then I had the good fortune to be able to correlate this thing they refer to as stimulated pore volume or stimulated reservoir volume, this SRV, with that. It works. Well, that's really neat because I've now introduced to you the idea that I can interpret, evaluate in a constructive way anisotropic systems. Because that's pretty anisotropic. It's also heterogeneous. But I can interpret it, and this is the natural fracture system, and this is the matrix. On the log-log type curve, I see that kind of a signature. Now you say, well, that doesn't look like, well, go back and think about your Horner plot. That S-curve on the Horner plot, this is the storage. Oh, that's storage. We're going to ignore it. That signature right there is now what do we do? There we go. That piece of that signature right there is analogous to this guy. They are really the same. Now, the physics that caused that one is different, but the actual behavior of the system is identical. That is, quote-unquote, storage.
That's a pore volume of the fracture?
Yes. It's the
Not
pore
actually fractured.
Well, the question is, back up, is that the pore volume of the fractures? That apparent storage, which in this setting we would interpret as storage. I have come to believe it is not storage in that sense. The problem here, on the Horner plot, for example, this actually is, if you use, there's a really great book called Fluid Transients, written by Wiley and Streeter. In Wiley and Streeter, they show that this data is actually usable. You can calculate very important, well, one of the goofiest things, in Wiley and Streeter, they show that you can use this data to calculate top of cement. For all the drilling you see the crowd, top of cement. This signature includes, because of the way that pressure waves change, they change speed. And because they change speed, depending on how the casing is held, you load that. The storage signature actually includes the overprint of where top of cement is. It's usable data. When we do pressure and that pressure transient analysis, we ignore that. In fact, it's ignored. You know, we play it like it's useless. In fact, when you look at Wiley and Streeter, you'll discover that this actually has useful information in it. Well, and that's my thesis to you here. This, which we would normally completely ignore because we're only going to look at this steep part, I have come to know that that is useful data for the same reason. It's predicting for us the effective conductivity of the fractures, plural, the ones we paid money for, plus the ones that Mother Nature created. Okay? So it's both. The bad news is, I have not been able to convince myself that I can separate the two pieces. That I can say, okay, this part of the, that part right there is the stuff I paid money for, and that part's what another, I don't think I'm that good.
Sure.
Yes, please.
I thought like the top is curved and the one in the bottom is straight, right?
Goes back on amazing drawing it. No, they're probably, in reality, they're not.
What Dave or
So,
Ron?
I'm sorry, the question was, why does this line have curvature here, and this one is straight?
No, the one on the
Which? I'm sorry. Come show me.
yeah, the one in the bottom,
Here,
and the other one,
the top.
this one is straight, and the other one.
Oh. All right. Well, two arguments. First of all, let's deal with this line. This line is straight here and here. In reality, they're not. Okay, one or both of them will curve, right? But the reason this one is curving here and this one is straight is, if you notice, I'm basically right at the log of time as well. Right? So on the log plot, on the semi-log plot, this becomes straight, but on the other plot, on the log plot, it's still curved. So it's just simply a transformation from log to semi-log. Okay, good. All right? Go another step. Wellbore storage. If I indeed had wellbore storage on the log-log plot, I would see a straight line with a unit slope. That 45-degree line we talked about, et cetera, et cetera. Here it should show up as a unit slope line. Unfortunately, in the semi-log setting, it's just going to be a slightly more curving signature. Yeah, that's life. It's okay. Bottom line is, if you use that other more elegant mathematics, there is useful information in there about your tubular goods, about the perforations, about the cement. You know, there's a lot. Well, one of the things, interestingly enough, sometimes on buildups, you'll actually see this thing have slope, different slopes. You know, it'll be approximately 1.2, and it'll break to 1.1, 0.9, all close to 1, but not equal to 1. I told you, isothermal, which is the assumption that it creates a unit slope line, is not necessarily valid. The temperature may not be constant. One of the things you'll often see is an overprint due to changes in density. It is very common in both oil and gas wells. Consider, for example, you had an oil well, you're doing a buildup, the pressure wave is moving through that system. Which is the more dense fluid? Oil or water? Water. Therefore, most likely the oil is sitting on top of it. Speed of sound is related to density. Therefore, I have a gas column sitting on top of an oil column sitting on top of a water column. I could readily imagine the speed of the pressure wave moving through that system is going to change. And that's what wellbore storage is all about, is the speed of the pressure wave in the system. So I could imagine that as the pressure wave moved through this thing, if I had really good data, I would see the slope of this change because the speed of sound, therefore the apparent permeability, changed. And indeed, sometimes you can. So this actually has very useful information in many cases. It can give you some very important clues about water-oil ratios, how they change, what have you. All right? Enough. Fracture cleanup. One of the things that we look for, the question was raised a minute ago about what can happen. Why would I do this? Well, one of the big issues is the different signatures wells exhibit after an acid job or after a frac job. The goal would be to try to maximize productivity, which is pushing the line as far south as you can get it, and as shallow as you can get it. Well, if you were to look at data sets, and this is really driven by some work that I got to do looking at different breaker systems in the frac jobs. The value of the difference between those two lines in this particular study was about $1 million per well. And the only change was the type of breaker that they used in the frac job. $1 million difference in EUR, and the difference was the breaker that was used in the frac job. So the objective would be to try to get maximum productivity as quickly as possible and force the line as far south as possible and have it stay put. Well, that's what we're going to look at for the early time stuff. Fracture cleanup. If I try to produce this graph right here those two graphs, those two graphs are worth, listen carefully, those two graphs are worth $1 billion. I'm not kidding. The company that saw and recognized the significance of that signature is now actually worth about $14 billion. But the actual transaction that arose as a consequence of those two graphs, the first one was $480 million, and about 2 weeks later, they then bought another company worth $520 million, the sum of which is $1.0 billion, Baker Lilly. Just because they recognized that these wells that had this signature were being forced too much pressure was being, too little pressure was being put on them. They were producing back the frac jobs. They were producing back the frac jobs. They had good frac jobs, and then they produced the well so hard, pulled it down so hard, that the frac job basically was destroyed, and it caused the well to get worse. Because remember, up is bad. The well would get worse. When compared to wells that were produced very gently, the slopes of the lines were the same, but the gently produced wells were sitting down here on this graph. That increment basically was worth $1 billion. Please.
Is there any situations where you produce a well too conservatively that you actually hinder your production?
Well, how do I answer that with a straight face? It's a legitimate question. The answer is yes. The obvious trivial solution is you don't produce it at all. You're never going to hurt the well if you don't produce it. There is a conception, a belief, they refer to it as shake and bake, or rest and test, marinate the well, and basically that's the idea of what they're arguing is they say, well, gosh, we're not even going to produce the well at all. They will leave it shut in for an extended period of time, and that will improve it. That's foolish. The well has to be produced to maximize its production. That's an oxymoron in the extreme. It has to be, we can produce it too hard, and we can produce it too gently. The trade-off is, producing it too hard means we put too much pressure drawdown on it, made it sensitive and damaged it because of stress issues. If we produce it too gently, we're not removing those fluids that will create changes in relative current